In this video, we're going to explore exponential transformations. We're going to focus in on this problem here, number 37 at the bottom, and we'll take a look at how each of those transformations are affecting our exponential graph. So we have here that we're going to graph y equals 2 times 3 to the x plus 1 minus 4. Let's take a look at each of those transformations over on Desmos. So what we have here is our original parent function, which is y equals 3 to the power of x. Now, if you think about what exponential properties they have, hopefully you can see that some easy points to test would be the point like if you plug in x is 0, then y is 1. Anything to the 0 power always gives us 1. And likewise, we can also say we can plug in 1. That's a nice easy number to plug in. So when x is 1, we get the value of 3. So these are going to be your 2 points that you want to plug in all the time for exponentials. Those are going to be the nice easy points to plot. And then from there, that's what you're going to be moving around. So let's apply the transformations. First of all, our first transformation you can see has the a in front of the equation, a times 3 to the x. And so as we set this up, we can see that as a moves, our graph is actually going to be stretched vertically. You can see here that each of those points are being stretched vertically. We're pulling it up, kind of like that Play-Doh example I had given before. Okay, so as we do this, as we pull it up, what we see is that the 2 points we have, 0, 1, and 1, 3, now get pulled up to 0, 2, and also 1, 6. Very similarly to how we had discussed how the y values are affected, we can see that because these points are pulled up, we can see that each of the y values are being multiplied by a value of 2, right? The 1 times 2 is what gives us 2, and 3 times 2 is what gives us the 6 there. Well, that's why we have the a value, which is 2, right? We're seeing that the y value is getting multiplied by 2 there. Okay, so that's what's happening with our value in front, the a value. As we take a look at our other graphs, I'm just going to move this along. So now we're going to fixate y equals 2 times 3 to the x. Okay, and then what we're going to now do is apply some shifts. Okay, so we can see now that here we have y equals 2 times 3 to the x still. H is currently 0, but as I move the h, we can see that what the graph does is it's actually going right and left. We're just kind of moving that graph left and right. And you can tell because based on your knowledge of transformations, you know that any h value directly connected to x is what's going to move the graph left and right. And it moves it appropriately. If h is 1, then it's going to move left 1. If h is 2, it moves left 2. If h is 3, it moves left 3. Likewise, if you have the negative values, let's say it's x minus 1, it's going to the right by 1, right by 2, right by 3, right by 4, and so on. Okay, so it all has the same kind of functionality properties as you have been accustomed to seeing in other transformations. All right, so in our example that we had on the notes, we're moving it technically left by 1. It says x plus 1 there. So we're going to go ahead and move it left 1. And you can see here, remember what we want to do is take the points that you are always fixated on. In this case, it was 0, 2, and 1, 6. And notice that as we take a look at 0, 2, and 1, 6, those points are now going to the left by 1. So now our new points are going to be located at those locations there, right? At negative 1, 2, and also at 0, 6. So let's go ahead and label that then. We're going to label the points negative 1, 2, and 0, 6. Now that we have moved our horizontal shifts, let's go ahead and move our vertical shifts. So now the k value, we see that in number 37, we're going down by 4, negative 4. So we're, again, we can go down. We can see the graph move down. Or also the graph can technically move up if you want as well. Okay, so back at the original location, we're going to move down by 4. So 1, 2, 3, 4. There we, oops, moved it too much. Okay, so there we are at negative 4. And when you do that, you're also moving the other points down by 4 as well. So negative 1, 2, and 0, 2 will be your new points. How do we get those points? Well, if you look at the graph, examine the 2 points that we had originally, we can see that those points are going 1, 2, 3, 4 units down, and then this point was going 1, 2, 3, 4 units down. Okay, so you just take those points and move them down by 4. Okay. Now, as we move the graph, there's also something important that we should keep in mind. You're not just moving the exponential growth graph, you're also moving the asymptote. You can see here that we have the asymptote because the exponential curve originally has an asymptote along the x-axis. It can never touch the x-axis, right? Because y can never equal 0. Well, as you move the graph down, the asymptote moves down with it as well. So for that reason, you also need to be aware that there is an asymptote at this location at y equals -4. So that's something to be aware of, that when you draw your exponential growth graph or exponential decay graph, that you should not be having your range go all the way down to -infinity. It does stop at -4. Okay, so that's one thing to be aware of. All right, and then the last thing that I also wanted to show you was how, going back to the original, there we go. So our original graph of y equals 3 to the x, I have another label here, take that off. Okay, oops, I have another label somewhere else, right here, -1, there we go. Okay, so our original graph of y equals 3 to the x, if we compare that with y equals 1/3 to the x, we see here that this is going to be an exponential decay graph. We see that the 1/3 compared with the y equals 3 to the x, this 3 is a value that's greater than 1. And the 1/3 is a value that's less than 1. So if it turns out that you have some kind of base value that is less than 1, we see that we're going to have an exponential decay graph. If that base value is a value greater than 1, then that's when you have the exponential growth graph. So do be aware of that. Not only that, but if we take a look at y equals 3 to the -x, let's see what that graph looks like. Oh, it's overlapping our green graph. Why is that? Well, if we take a look at some properties of exponentials, 3 to the -x is technically the same as the reciprocal, right? Turning a negative exponent into a positive, which is the same as 1/3 to the x. And if we just rewrite that, technically since we have a 1 on top, this is the same as 1/3 to the power of x. They're the exact same graph, and that's why they overlapped each other. Okay. So let's go ahead and go back to our notes. We have a couple of things that we had found out in number 37. Hopefully through the Desmos activity, you were able to draw your graph right there. But now let's go ahead and determine the domain, range, and horizontal asymptote of the graph. Well, we saw that the graph was extending in both directions, right, as we were looking at the graph. Let's go back to it right here. Okay, and then the k value was at -4 right there. Okay. Let me take off all the other graphs so that way it's less confusing for you. Oops. Each value was 1, and then take off that graph. Okay, so there we go. So we can see that the graph does extend in both directions in terms of the x value. So we're going to go ahead and say that the domain is all real numbers, of course in interval notation. So we say -infinity to infinity. What does the range look like? Remember what we said about the asymptote. The graph does have the asymptote occur, right? It has to stop at that bottom line. So we know that we cannot have values any lower than -4. But the y values do go up from there. So the range value, in this case, would start at -4, non-inclusive, and go up to infinity. Our horizontal asymptote, we found, was at the y value of -4. That was our green dotted line right here. Our green dotted line was at y equals -4. And it looks like that's it. So one other thing that I would ask you that you do, remember, make sure that you have the proper graph. So in terms of the proper graph, you should have had your labels at -1, -2, and 0, 2. Okay? -1, -2, and a 0, 2, with the y horizontal asymptote at -4. So your graph would have looked something like that. But when you did this in the video, make sure that you also draw the other graphs to show how you got to this final graph. All right, let's go on and just describe in general what are the properties of exponential functions. In this case, what we're looking at is we are looking at exponential decay in this case. You do see that a value is between 0 and 1, but remember that some of these properties will also hold true to exponential growth. Remember that exponential growth occurs when the a value is greater than 1. All right, the domain is the set of all real numbers, or we know that for either exponential decay or exponential growth, the real numbers are always going from -infinity to infinity. That doesn't change. The range is the set of all positive real numbers. We can see that it's always above our x-axis because there's an asymptote there. So we also say that in interval notation, we're going from 0, non-inclusive, to infinity. How many x-intercepts do we have? Well, because there's an asymptote here, we can never have any x-intercepts. So there are 0 x-intercepts. And the y-intercept is always going to be right there in this location, which is at the point 0, 1. Okay, because if you ever take an equation, a to the x, and put 0 in there, you'll always get a value of 1. The x-axis, or that's basically the same thing as y equals 0, is our horizontal asymptote as x goes to infinity in this case. Okay? Because it never touches the x-axis. Number 4, f of x equals a to the x. Again, we're talking about exponential decay. A is a value between 0 and 1, is an exponential function and is decaying, or decreasing. Let's call it decreasing. The graph of f contains the points. Let's see, what do we have? We definitely have the point 0, 1. We also talked about an easy point you can plug in, which is the point 1, and then what value do you get? Well, if you plug in 1, you're going to get the value of a. And you also have the other point where, I guess if you want to make it a -1 value, then you'll get the point 1 over a, because that'll be its reciprocal. The graph is smooth and continuous. Okay, I'm going to go back. I'm going to backtrack one page here, and let's just do one problem right here where we're dealing with some points on the graph. And what we want to do is figure out what that equation actually looks like. So here we have given f of x equals a times b to the x power. Find f of x if f of 0 is 5 and f of 3 is 40. Well, if we know that our basic function is a times b to the x, then in this case, x is 0 and y is 5. So if we plug that in, we get 5 equals a times b to the 0. Now we know anything to the 0 always gives us 1, so basically a is 5. If we plug that back into our equation, we can say that y is now equal to 5 times b to the x power, and now we're going to plug in our second point, where we know y is the value of 40, that's our output, and b is the value that we're trying to find, because the 3 represents the x value. Oops. The 3 represents the x value. So in solving for this, we can divide both sides by 5. We get that 8 is equal to b cubed. So what b cubed, what times what times what, gives us the value of 8. Hopefully you're saying that's the value of 2. Okay? So in this case, what we see is that our function f of x is equal to, let's plug everything in, the a value is 5, the b value is 2. And there's your equation, like that. All right, that'll conclude our video for today.